here today to talk about the Cretaceous Las Vegas. Thank you.
Thank you, Sally. So the main event today is the unveiling of this beautiful painting by Daniel Trujillo and Tiffany Pereira. And so I'm sort of the warm-up act. What I want to do is put their painting in context so that when you see their painting after my talk, you'll have a little understanding of how we got here. I think when those of us who do paleontology love being out in the field collecting fossils and trying to figure out what they are and how old they are and putting it all together. And I think that the final goal is to tell a story of how all these animals and plants fit together into an ecosystem that existed here in southern Nevada in the distant past, around 99 million years ago in the case of the Cretaceous rocks. But we've also, in the last couple years, learned quite a lot about earlier dinosaurs that lived here in southern Nevada. And this is the first time, as far as I know, that I or anybody else has taken the opportunity to kind of combine what we now know about the dinosaur history of southern Nevada. Dinosaurs are not especially abundant in our state. You cross the line into Utah, and the dinosaurs seem to be falling out of the cliffs. So I have a little bit of dinosaur envy of my colleagues in Utah, because they've just got literally, I think the highest diversity in the world is in the Grand Staircase Escalante National Monument. One consolation is that it's my former student, Alan Titus, who is the paleontologist there, so I can sort of vicariously enjoy what Alan's doing. So we don't have quite as diverse or abundant dinosaur fauna here in southern Nevada, and I want to help explain why that is, and explain what we have learned about the dinosaurs. So before I get all wrapped up in that, I want to say a few acknowledgments. There are several people. The research I'm going to be talking about this afternoon was done by quite a range of people. These are the main people involved. Josh Bondi, my former PhD student at UNLV, who's now a visiting professor in my department, very active, and many of you know Josh. He's really the dinosaur guy who's discovered more dinosaur fossils in Nevada than anybody. His former master's thesis professor at Montana State University, Dave Riccio, was involved, especially in the early stages of the Cretaceous work in Valley of Fire. Heather Stoller, one of my master's students, just graduated in December, who did a lot of trackway work. Don Reynoso, another one of our grad students at UNLV, who got the dates for the fossils, the rocks in Valley of Fire that I'm going to describe. And my colleague and friend Nick Sains, who's in the front row, who's just been a great colleague to kind of keep my interest up and read my manuscripts and proofread and go in the field with and so on. So these are people who've all been involved, and there's probably a few others who I could have mentioned as well. Also, I want to take this opportunity to, because we're going to be talking about two different kinds of dinosaur fossils today, footprints and bones and teeth, I thought it'd be a good chance to kind of explain the difference between body fossils and trace fossils. And they're really quite different. Body fossils are fossilized portions of the body of an animal or plant, such as a bone, tooth, or leaf impression, or a piece of petrified wood. So you can actually see what the body or a portion of the body look like. And that's what most people think of when they think of dinosaur fossils or any other kind of fossils. There are also trace fossils, which are footprints and burrows and coprolites, fossilized dung, and those sorts of things, which doesn't necessarily tell you what the shape of the animal was, but it tells you that there was an animal that went there, that was there at one point. In this case, we're talking about dinosaur tracks or footprints. So, so I'll be giving examples. In the Jurassic, the slightly older rocks and fossils, the whole record is trace fossils. In the Cretaceous, the whole record is body fossils. So here's a little stratigraphic column by a wonderful artist named Ray Troll. And the part of the column in which dinosaurs occur is in this green part, the Mesozoic era, particularly the Jurassic and Cretaceous. Dinosaurs first appear in the fossil record in the latest Triassic, but only in a few places. So for all practical purposes, dinosaurs occur in the Jurassic and Cretaceous. then they became extinct except for the birds, which are literally feathered dinosaurs, but we'll not pay attention to those today. So we're interested in Jurassic and Cretaceous. And so the first thing that a paleontologist does, if he or she is interested in finding fossils of dinosaurs, say, is to find out where there are Jurassic and Cretaceous sediments, because you have to have the right age rocks if you're going to find dinosaurs. I get people fairly often bringing fossils into me at UNLV that they collected in Las Vegas Valley that they think are dinosaurs. And I can almost tell them, as soon as they tell me where it came from, I can usually tell them that it's not a dinosaur because it came out of the wrong age rocks. So Jurassic and Cretaceous rocks, this is a geologic map of Clark County, most of Clark County, and each of the colors represents different age rocks. And so you can see that Jurassic is the greenish color and Cretaceous is this tan color. So you've got to look for green and tan if you want to find dinosaurs, and we don't have a lot, actually. There's a little bit of green over here we'll talk about, and then there's some green and tan over here in the eastern part of the county. But most of Clark County has rocks that are either older or younger than the Mesozoic rocks. And so that's one reason we don't have lots of dinosaur-rich deposits in Clark County, is because we don't have a huge amount of rocks of the right age. Over in Red Rock Canyon, there's a big splotch of green right there. That's Jurassic Aztec sandstone. So that's where we're finding, among other places, the tracks. So the big red rock cliffs of Red Rock Canyon are Jurassic sandstones. So we find tracks in there that we've been finding for the last 2 years. Gary Smith is in the audience today, who's one of the guys who found the first, I guess the guy who found the first dinosaur tracks in southern Nevada, out in Red Rock Canyon back in 2010. And then the other place where we find the right age rocks is over in the Overton Valley of Fire area. So there's Overton, here's I-15 here going up toward Utah. And so it's in this general region that we find, most of which is in Valley of Fire State Park, where we have Jurassic and Cretaceous rocks. So my talk today is focused on the Valley of Fire rocks, because that's where the rocks are that we're finding these dinosaurs. I'm not going to get into the dinosaur tracks in Red Rock Canyon, which are more or less the same ones that we're finding in Valley of Fire, but just kind of focus on Valley of Fire this afternoon. So then, now a little bit of paleogeography. So of those three periods of the Mesozoic era, Triassic, Jurassic, and Cretaceous, the continents of the world were doing all kinds of interesting things. So in the Triassic, when dinosaurs first appear on Earth, all the continents were massed together as a supercontinent called Pangaea. So here's North America here's South America and Africa. Europe is not too far away over there. And so the Triassic, which we're not going to focus on this afternoon, was a time where this one huge supercontinent, and that affected the climate and the types of rocks that are deposited here and so on. As we move into the Jurassic, this supercontinent is breaking up. So here you can see the North Atlantic starting to open, also the South Atlantic between South America and Africa is beginning to open, and that changes as soon as you start separating the continents. Then the air masses change, the climate changes. A mountain belt is developing on the western edge of North America, which affects the drainage patterns and rain shadows and so on. So that rain shadow, in fact, that was created in part by the uplift of the ancestral Sierra Nevada mountain range is what caused the sand dune deserts of the Aztec sandstone that we have so beautifully exposed in Red Rock Canyon, Valley of Fire, and a few other places. So here's Valley of Fire, the red rocks, red and whitish rocks of the Aztec sandstone. So first I'll talk a bit about the dinosaur footprints that we're finding in those rocks and what they are telling us. So here's a story actually from the front of the B section of the RJ back in November of 2011, just a little over 2 years ago, 2 years and 2 months ago, announcing dinosaurs hiked Red Rock Canyon. So this was actually the first discovery of trackways that Gary Smith had discovered, and finally Nick Saines, who's documented, and this is actually a track that Nick himself found when he was going to verify that what Gary and the other hikers had found really was tracks. So this really opened the floodgates of interest in southern Nevada on tracks, and lots of other hikers then got interested and said, oh, I've seen stuff like that, such and such a place. And so we now have maybe 20 different track sites, not all dinosaurs, several dinosaur sites, as well as other kinds of animals that I'm not going to take the time to talk about today. So this is all quite new. Certainly the trackway research is quite new. The bone body fossil research is a little older, but still 10 years ago we didn't have any evidence of any dinosaur. So the discovery and explanation and interpretation of dinosaurs in southern Nevada is really a very new field that we're just really kind of getting our feet on the ground. So just to show you a few examples of Valley of Fire tracks, this is my student Heather Stoller, who just graduated with her master's in December, with some tracks on a face and on a boulder that tumbled down the hills in Valley of Fire State Park. You can maybe see some little footprints right there. So this is one of the dinosaur tracks that we've seen in Valley of Fire. There you can see a good representation of it. Dinosaurs typically have 3 prominent toes. They have four toes, numbered 1 through 2, 1, 2, 3, and 4. The number 1 toe is like a dew claw on a dog's front leg, and it's so up above the ankle, and you rarely get an impression of that dew claw. So the number 1 claw is missing here, and there's number 2, 3, and 4. And number 2 and 3 typically are farther apart than 3 and 4, so we interpret this to be a left foot. And the interesting thing about this particular trackway in Valley of Fire is that they're all left feet. So either this was a dinosaur with 2 left feet, or it was hopping, and that's what we think. We think that it had an injured foot and was actually hopping along. So this is an interesting track site in Valley of Fire State Park. Here is another site that at first glance is a cross-section through a layer of rock. Almost always when you're looking for dinosaur tracks or any other kinds of tracks, you look on bedding planes, the actual surface of the rock that was exposed as a bedding plane when the animal was walking there. But once in a while, you can find tracks which are exposed on a vertical face. And so here, all this little kind of disrupted bedding here that you can see in this exposure. That's what it looks like up close. This is another rock that tumbled off the cliff and is upside down. So I'm going to turn this slide upside down to show you what it looks like when it was right side up. And so you see this disturbed zone right here, which our interpretation is that the animal, the dinosaur, was walking along in dry sand. It's hard to make a well-preserved track in dry sand, and all of us have walked up sand dunes with bare feet probably, and you can imagine that you make a little pit in the sand when you remove your foot, but it's not something you would expect to be preserved in the rock record. The next windstorm that comes along is going to cover up your footprints and it'll be gone. But once in a while, an animal might imagine, if you have well-laminated sand, the animal steps into that sand, disturbs the lamination, like right here, and then when it removes its foot, as in the far right-hand view, then it leaves this kind of disturbed zone, which then is what we see in the record. So that's what we think this is. We think that this is a place where a dinosaur stepped down. That's 1 toe rather, and then another toe, and then the 3rd toe is right there. So once in a while we can see these kinds of cross-sections. We can't tell what the animal was other than it was a 3-toed dinosaur. At least that's our best guess. And you're only getting a kind of 2-dimensional view on it. The dinosaurs that were making these tracks in Valley Fire State Park, in the Jurassic, and this would apply also to Red Rock Canyon and elsewhere, are almost certainly bipedal theropod dinosaurs. So these are like this guy here, whose name is Coelophysis. Coelophysis is very well known from the Triassic, a little bit older, in New Mexico. A place called Ghost Ranch has dozens of these guys. And we don't know. The problem with footprints is that you can't identify the animal very specifically that made the footprint. As you can imagine, there might have been several different kinds of dinosaurs, all with the foot shape that was so similar that you can't distinguish among them. So the practice amongst those of us who study trace fossils is to put a name on the track, on the footprint in this case, that's completely separate from the name of the dinosaur that made the track, because usually you don't know what the dinosaur was that made the track. So we call these tracks Grallator, G-R-A-L-L-A-T-O-R. I think I've already had a picture of that, I think. Regardless of what the dinosaur was. So we like to be able to figure out what the dinosaur was that made it, but usually we can't. Okay, so that's all we can say about these wonderful tracks we've been finding in Valley of Fire and Red Rock Canyon, is that they were made by small theropod dinosaurs. So that's half a meter, about a foot and a half. So it was maybe 7 or 8 feet long, 3.5 feet or so tall at the hip. And so these are the kinds of dinosaurs that were wandering around here in the Jurassic. Probably a bit more diverse community a little bit farther to the east for reasons that I'll actually explain in just a few minutes. Okay, so that's what we know about the Jurassic. Moving up into the slightly younger Cretaceous is when we start picking up an actual bone record. So these are body fossils now, and these are the fossils that Daniel and Tiffany portrayed in the painting that you're going to be seeing in a little while this afternoon. So this shows the Paleo Geography in the Cretaceous, and it's hard to see what you're looking at here, but this is a big inland seaway up in the upper right, and here this vertical line, which is very hard for me to see, and I know most of you can't see it at all, is the border between Utah and Nevada. So Nevada is just the left-hand edge of this slide. Here's Utah and here's Arizona. And what you see here is that the drainages, this is a reconstruction by Ron Blakey of Northern Arizona University, who's become quite famous in geology and of making these paleogeographic maps. So what Ron Blakey shows is that the drainages crossing Utah, flowing northeasterly, continue, the headwaters were over here in what is now eastern Nevada. So the fossils that I'm going to be describing in just a few minutes from Valley of Fire in the Cretaceous were part of an ecosystem that is well represented in Utah, and we're just getting kind of the upstream edge of that represented in the sediments in Valley of Fire State Park. And here, that little arrow there shows approximately where Valley of Fire State Park is. And here's another one of Ron Blakey's maps showing the latest early Cretaceous. The Cretaceous is divided up into 2 epochs, the late Cretaceous and the early Cretaceous. And the rocks that we've got in Valley of Fire State Park are right about on the boundary. In fact, when Josh was first working on these as part of his master's thesis at Montana State, it was generally thought that they were lower Cretaceous or early Cretaceous toward the end of the early Cretaceous. As I'll describe in a few minutes, we now have some good radiometric dates which show that they're actually a bit younger. Now we know that they're late Cretaceous, not early Cretaceous. Not that that matters a huge amount. So the interesting thing in the Cretaceous is that there's a big inland sea that's coming. As you can see, it's connected with the Arctic Ocean here. So this big light-colored zone right here is a shallow sea that continued down, and a little bit later, I think the next slide shows. Yeah, a little bit later in the Cretaceous, that sea turns out to be what's called the Western Interior Seaway, which connects the Gulf of Mexico all the way with the Arctic Ocean. So you could have rowed a boat, in principle, from the Gulf of Mexico all the way up into the North Pole. And you probably could have, in terms of temperature and climate as well, because the Cretaceous was a very warm time. It was warm and tropical. So the environment here in Nevada and adjacent parts of Utah and Arizona were very hot, warm, tropical environments. No ice caps at all that we have any record of. So it was a very warm world. There are crocodile fossils that have been found way up in northern Canada, for example. So it was a very different world than we have today. And the reason for that inland sea is a really interesting one. That it turns out that part of the reason for that is there was a big plate of oceanic crust called the Farallon Plate that was being subducted. It's a cross-section through western North America. West is on the left, east is on the right. And this plate of oceanic crust was being pulled underneath North America, really deeper than this little cartoon shows, and kind of pulled the crust of the Earth down. So there was this big weight of oceanic crust that was pulling down the crust of North America, forming this big valley that was below sea level, so it filled up with water. So that was going on for roughly 30 million years or so in the late Cretaceous, creating this big inland sea, which is why in places like Nebraska and Kansas and Wyoming, you find lots of marine fossils in the late Cretaceous. And then along the eastern edge of that was wonderful habitat for dinosaurs. So this is a map that shows the situation in the late Cretaceous about, say, 90 million years or so ago. And what you see is that North America is divided up into two big islands. This long, skinny island here, which has taken on the name Laramidia. That's a new name to most of you, I suspect, because it's a fairly new name to me. Named after Laramie, Wyoming, is where it comes from, because Laramie, Wyoming is on this long, skinny island. So here's Laramidia, which goes from way up in Alaska all the way down into Mexico, fairly skinny island. And then there's this interior Seaway, and then on the other side of the Seaway is the other half of North America called Appalachia. It's the other island. This turns out to be, Laramidia turns out to be one of the most interesting places for dinosaur speciation and paleoecology that has ever been described. Tyrannosaurids evolved here, so T-Rex, for example, is well known from Wyoming and other sites up in the northwest. Ceratopsian dinosaurs like Triceratops and others diversified here tremendously. So a lot of this work has come out of Grand Staircase Escalante National Monument just within the last 10 years. So we're learning a lot about the dinosaur paleobiology of Laramidia. So for reasons that we really don't understand, this turns out to be just a nursery for generating new species of dinosaurs. And that's why our friends in Utah have such a wealth of dinosaur material to work with. Over in Appalachia, not so much. There are certainly dinosaurs over there, but not nearly the diversity, especially of Tyrannosaurids and Ceratopsians. Well, the other thing I want to use this slide to show is that the reason Utah and Wyoming, Colorado, have such great dinosaur habitat, or dinosaur fossils, is because the habitat was perfect. We had these coastal plain area, this kind of gray area, right along the edge of this interior seaway, with rivers flowing across it. It was apparently just perfect dinosaur habitat. Where we are in Nevada is just over in this mountainous area, just to the west of that low relief coastal plain, and it just was not quite as good. So the dinosaur fossils that we're finding in the Cretaceous of Nevada are just the upstream headwaters of some of these streams that continued across this coastal plain and then out into the central, to the western interior seaway. So that's the situation in the Willow Tank Formation that I'm going to describe in just a second. That's the same. So, okay, so let's talk about the fossils finally. And these are fossils mostly that I'm going to show. I think all of them, in fact, are ones that are on display in the exhibit that you'll have a chance to see. So this is a little watch glass that has some little tiny 2 to 3 to 4 millimeter size eggshells. And when you look at these eggshells, so there's some more you can see with a millimeter scale. And if you look at these eggshells with the scanning electron microscope, the structure in cross-section has very distinctive structure that is distinctive of theropod dinosaurs. Again, theropods are these bipedal carnivorous dinosaurs like T-Rex and Deinonychus and others. So the folks who've studied these, and this is not my specialty at all, in fact there's a woman at Montana State named Frankie Jackson who did the eggshell work. And so Frankie can identify these based on scanning electron microscope images as theropod dinosaurs. I should say, right now maybe, that most of the fossils I'm going to show and talk about, and you'll see in the exhibit, are pretty tiny. And we think of dinosaurs as, huge, fantastic monsters. The rocks that we're getting these fossils out of are stream deposits, floodplain deposits. And so that the dinosaurs died in the floodplain and were washed down the river in big floods, and the bones were scattered here and there and so on. And so we're lucky to get anything, and we don't get, the environment was just not suitable to get whole, intact dinosaurs. When I show some images from Daniel and Tiffany's painting in a couple minutes, I'll reinforce that. So we're lucky to get a few little scraps of eggshells and bones and teeth. And so the way that we work on these is to collect huge amounts of sediment and pass it through screens of varying coarseness. So you might start with a screen, so you stack these screens up. The uppermost one is like hardware cloth with a 1/4-inch opening or so that catches the biggest bones and rocks. And then the one underneath that is half that size, and you finally end up with like window screen at the bottom. And so you catch successive layers of bones and teeth with each layer of screen. And then you look carefully and hand-pick with a microscope these tiny little shells, throwing away all the miscellaneous rocks. So that's how these tiny little fossils are recovered. It's by this screening process. And here you can see in my hand a little piece of theropod eggshell. These are what we call sago palms. This is somebody's front yard here with some sago palms in my neighborhood. These are cycads, which is another type of plant which existed in the Cretaceous. And I don't know why my picture of cycads is not there, but I'll get to it. One of the biggest bones that the folks have found, and again, this is Josh Blondy's work mostly, is this piece of bone, which is a femur, upper leg bone rather, with missing the lower part. It's about 8 inches long. You'll see this on display in the exhibit. This has a diagnostic morphology of a theropod dinosaur, very similar to Deinonychus. Deinonychus is one of these very spectacularly voracious-looking predatory dinosaurs, which had a claw that looked like it could disembowel its prey in a matter of seconds. So we know from the shape that this is a theropod dinosaur, but we can't tell for sure any more specifically what it is, beyond saying it's a theropod. And that's a recurring story here, is that we can identify from the teeth and the eggshells and some of the bones generally what category of dinosaurs it was, but we can't specifically say this was Deinonychus or Tyrannosaurus or any other genus. Among the plants are Magnolia leaves. This is a magnolia from my neighbor's tree that I just photographed the other day, just to remind you what a magnolia leaf looks like. There's a leaf. Magnolia is a really interesting plant in that it's one of the earliest flowering plants. In the early Cretaceous, so these rocks from Valley of Fire are in the earliest part of the latest Cretaceous, and just before the sediments deposited in Valley of Fire, flowering plants experienced a big diversification episode. So not too long before that, there were no flowering plants on Earth. The flowering plants appear in the late Paleozoic, and then in the early Cretaceous, they just take off and start appearing all over the world. And magnolia is one of the earliest flowering plants. It's a very simple structure. The petals look very similar to the leaves, so it's a primitive flowering plant which is still successful today, native to North America and Asia. This is a painting I really like. It's actually a hand-colored lithograph from the Himalayas, a representation of magnolia in the Himalayas from a folio constructed or produced by a famous botanist named Joseph Hooker in the 1850s. Joseph Hooker was one of Charles Darwin's closest friends. And so just to remind you what the petals and the leaves look very similar to one another. So this is magnolia. It's a very primitive plant. Oops, and somehow my picture of the magnolia leaf that's in the collection got lost in that slide. slide, I don't know what happened to it, but you'll see it on display in the exhibit. Another thing you'll see on display in the exhibit is this tiny, tiny little tooth that's just a half a centimeter long or so, a few millimeters, and this is very diagnostic of also of a theropod dinosaur tooth. Again, we can't tell for sure what genus or species of dinosaur it is, but it's diagnostic, the morphology is diagnostic of theropod dinosaurs. And now here, finally, is one image. It doesn't do justice to the painting, certainly, but the image of that ecosystem where Daniel and Tiffany took all the information that the paleontologists were giving them, all the different kinds of dinosaurs and plants and turtles and so on, and put it together to form a painting. So I'll show you different portions of that over the next few minutes. So here, for example, is a Dromaeosaur dinosaur in a very tight spot. The Dromaeosaurs are a type of theropod dinosaur, which are the ones that are ancestors of birds. And so Daniel and Tiffany put feathers on these guys, so the tail is kind of feathery. There's little feathers coming off the head, it looks like. And we know from certain fossils in China that, in fact, not only did Dromaeosaurs have feathers, but other dinosaurs did too. So it's not become quite well known now that many different groups of dinosaurs had feathers. So this guy is being consumed by a big crocodilomorph. True crocodiles hadn't evolved quite this early into the earliest part of the late Cretaceous, but there were ancestral forms that are loosely called crocodilomorphs. So we know that there were some big crocs that were almost certainly hunting some of these animals. And then here is a sauropod dinosaur. Sauropods are the big plodding dinosaurs like the Diplodocus brontosaurus, which isn't a formal dinosaur name, but it's a common name that most of us know. And we also know from similar kinds of evidence that there are teeth of sauropodomorph dinosaurs. So we again don't know for sure what the name of the dinosaur was, if it's even one that has been named. And this research is ongoing, by the way, so hopefully over the next few years, we'll learn more. But so Daniel and Tiffany put in, appropriately so, of course, a sauropod dinosaur. We know there were some sauropod dinosaurs. The sauropods are best known from the Jurassic. So that by the time you get into the Cretaceous, they were not as abundant as they had been in the Jurassic, but they were still around. So we know from the teeth that there were sauropod dinosaurs, so there's one right there. And here's the magnolia. This is a magnolia tree that's in the painting with some wonderful birds perched in the tree. And here's a stegosaur. Stegosaurs belong to the group of dinosaurs called armored dinosaurs that include ankylosaurs and stegosaurs. And similar story, we know from the teeth that there were some armored dinosaurs. We cannot distinguish exactly which genera were present. So it could very well have been a stegosaur or an ancestral stegosaur. And so it's a reasonable guess that there were stegosaur-like dinosaurs running around in this ecosystem in Valley of Fire. And the plant communities include a variety of things. Here are some water lilies, members of the water lily family that have been found in the fossil record. Some equisetum, which is called horsetails, which are still around in the world today. So we're seeing some, and the equisetum is not a flowering plant. The water lily, of course, is, but equisetum is a very old genus of plants that's been around for a long time and still doing well today in certain environments. Two bones that are connected to each other or lying adjacent to each other. They're scattered hundreds and thousands of meters downstream and just highly distributed as it happens. Here's some more equisetum and another turtle. More water lilies, and there's a variety of ferns and fern-like plants. You'll see some of those on display. And then here's the whole scene, as well as I can show it on a small screen, showing the relationship between all these animals. Let's see. Here's some other plant. Here's equisetum. serrated on the margins. It's just very similar to modern magnolias. This whole thing is doing funny things. I'm sorry, I don't know what happened. I'm missing a slide. Okay, so there's a couple things I wanted to talk about that I actually had slides for that somehow or other got lost between when I drove over here and now. I don't know what happened. So one has to do with dating. And so how do we know the age of these rocks? In Red Rock Canyon Valley of Fire in the Jurassic, the Aztec sandstone is actually poorly dated because we don't have any ash beds that are interbedded with the dune deposits. So there's nothing to date. You can't just date it. Radiocarbon dating can be used for very young fossils like mammoths and camel bones and so on that we find out in upper Las Vegas Wash and Tule Springs, if they're not older than 50,000 years. But after 50,000 years, radiocarbon dating is no longer viable. All the radiocarbons are already decayed away. So we're dealing with 100-million-year-old fossils here. So that's way orders of magnitude too old for radiocarbon dating. So what we have to use is other forms of radiometric dating, and the technique that we most commonly use is called argon-argon dating or potassium-argon dating, where we date little crystals of feldspar that are in volcanic ash beds called sanidine crystals. So these sanidine crystals have lots of potassium, and they, once the crystal crystallizes in a volcanic eruption, the minerals are trapped in the crystal lattice, and the potassium-40 decays to argon-40, and by zapping the crystal, taking a little crystal of sanidine and putting it in our lab at UNLV, we can zap it with a laser and vaporize that crystal and suck those vapors into a mass spectrometer and determine how much argon-40 is present. And we know there was no argon-40 originally, and that we can get a date. So, for example, these rocks out in Valley of Fire State Park have been dated to be 98.6 million years old. Now, actually, 98.64, I think it is. So, really quite precisely to the nearest 100,000 years. And furthermore, there's two ash beds in the Willow Tank Formation. The Willow Tank Formation is the deposit in Valley of Fire where all these body fossils that I've been describing this afternoon have come from. And there's an ash layer near the bottom, and there's an ash bed near the top, which allows us to bracket the age of the deposit. And the one at the bottom is 120,000 years older than the one at the top. So I guess one of the points here is that we have amazingly good precision with our radiometric dating if you have good material to work with, and these sanidine crystals and these ash flow tufts, or ash fall tufts in some cases, are really very good. We just don't have those crystals, those kinds of datable materials in the Aztec sandstone. So the Aztec, we have reason to think, because of regional correlations and so on, is around 170 to 180 million years. But in the case of the Willow Tank Formation, we can very specifically say that it's about 98.6 million years ago that these rocks were deposited, which was a surprise actually when we got those dates a couple of years ago, because as I mentioned earlier, Josh had previously thought, based on the plant fossils mostly, the plant fossils were characteristic of early Cretaceous, but the radiometric argon dates came back earliest late Cretaceous, the Cenomanian age of the late Cretaceous epoch. So we now know quite precisely how old those were. So to summarize, and I had a summary slide that just got lost somehow. I just don't know how that happened. But to summarize, so what we know about dinosaurs in southern Nevada is that there were theropod dinosaurs in the Jurassic, wandering around in these sand dunes, probably hunting smaller little proto-mammals that we also have tracks of, but I didn't show you those tracks today. And then in the Cretaceous, that sand dune environment had disappeared, and we became part of the headwaters of the streams that were draining into the western interior Seaway. And so the dinosaurs, which are so abundant in Utah, continued on up here into southern Nevada, and we're seeing examples of those. One of the most exciting, just to sort of end this here on an exciting note, is the Tyrannosaurus. Tyrannosaurus is the same group of theropod dinosaurs that Tyrannosaurus rex belongs to. Tyrannosaurids have their earliest origin in Laramidia, this long, skinny island that we were part of in the late Cretaceous. And basically in the mid part of late Cretaceous is where we see a big diversification of Tyrannosaurids. Here we're getting at least one tooth of a Tyrannosaurid in the very earliest part of the late Cretaceous. There are similar teeth coming out of a formation in Utah called the Cedar Mesa Formation. But this occurrence in the Willow Tank Formation is just as old as those in Utah. So we're seeing the very earliest evidence of Tyrannosaurids anywhere in the world right here in Valley of Fire State Park. So it's really exciting stuff, and we're continuing to work on it. And I think now I'll end and turn it back over to Sally and get ready to go unveil our painting. Thanks very much. Questions, I'm happy to answer a question or two. Yeah, Nick?
All right, question. You know, when we see the tracks, we say we really need body fossils to get the name of the species.
Right.
People ask that all the time. I didn't know that. How many body fossils do you need in order to get the species name?
It depends on what you. The question, if you didn't hear it, Nick, my friend Nick here, who works with me on some of this stuff, is asking how much, frustratingly sort of, we aren't getting any body fossils in the Jurassic rocks, we're getting lots of trackways, but we can't put a name on the animal unless you have a bone that identifies what it looked like. And so the question Nick asks is how much bone material do you need, I guess. And it depends on what you get. If you have a skull, the skull is the best. So if you have a skull that's intact, then you can work with that. The skull is the single most useful taxonomic part of any vertebrate animal, almost all vertebrate animals. So if we're lucky enough to get a skull, then we can work with that. Second to that is maybe a nice, well-preserved long leg bone or something. But the problem is that dune environments are not very good for preserving fossils. And they're so porous that even if an animal gets, let's say an animal dies and the dune collapses and buries it, which probably doesn't happen very often, is so porous that the bones don't last very long. I'm guessing there are teeth out there. If we had a big screening project and we screened, tons of sediment, we find some little teeth. I mean, they've got to be there. And so there must be body fossils out there. We just haven't looked hard enough yet. But they're really, really scarce. And again, it goes back to the environment of deposition has to be, ideally, should be conducive or suitable for preservation of the fossils. And you have to bury the fossil quickly and keep it away from the predators and the scavengers, and also to protect those bones from kind of weathering away with water passing through it and so on. So the dune environments just don't seem to be very conducive for that. So it depends on what kind of bone, to answer your question, it depends on what kind of bone we had. If we had one good skull, that probably would be enough to put a name on it. Other questions? Bert?
Yes, I wondered if the habitat for dinosaurs extends further south into Latin America or South America?
Yeah, almost certainly it did. In fact, among the best fossil beds in the world in the Cretaceous are in Argentina. So South America had their own dinosaur fossil assemblage. I don't have a good map to show it, but much of the time South America was separated from North America during the Mesozoic. And so it had its own isolated population of animals which are somewhat different than the ones in North America. So yeah, our island of Laramidia went down into northern Mexico, and that was about the end of it. But yes, definitely there was dinosaurs in South America.
Are they able to determine the size of the dinosaur with the prints that are established in the scrap beds that you're talking about?
Yeah, we can. Well, the thing about the question is, can we determine the size of the dinosaurs from the footprints? Birds and dinosaurs, and birds really are a type of dinosaurs, do have this useful property that the leg length and the hip height particularly is directly proportional to the foot length. So we can measure the foot length in the track, and that tells us the hip height. And if you have the hip height, then you can do a couple things with that. First of all, if you have a good series of tracks, then you can measure the stride. The stride is from one right foot to the other right foot, or left foot to left foot. If you know the stride and you know the hip height, you can calculate how fast the animal was going. So we can do that. And also you can reconstruct roughly how big the animal was if you know the hip height. So yeah, we can do that. And that one Coelophysis that I showed, which is about 6 to 8 feet long, is about the size of the larger of the dinosaurs that we're getting in Valley Fire and in the Aztec Sandstone and Red Rock Canyon. So there are in the Navajo Sandstone, which some of you may know, the Navajo is really the same interval of rocks as we have in southern Nevada, that we call the Aztec. In Utah and Colorado, they call it the Navajo. And those rocks have been studied for a lot longer. And maybe there's a little bit more diversity of habitats there. And so they have some larger tracts also. They have the same size tract called Growlator that we have here, and they also have some larger ones, which are called Eubrontes. So there were some larger dinosaurs, at least in the same age rocks over in Utah, that we haven't found any Eubrontes yet. So there actually is this track site that I recently have seen that may not be Eubrontes, but maybe something else completely different. So I'm working with some folks on some of those. So there's, you know, and as Nick and I and our colleagues spend more time, and all you guys who hike out in Red Rock and other places, you know, keep your eyes open. Well, I think over the next, 10 years from now, we're going to know a lot more. Thank you. Next time. Next. Anybody else? Yes.
I remember, the years we go to the Museum of Natural History in New York City, and we go into this, and we beautifully put together the dinosaurs. How did they know? Where did they put these things together to know that this is all those bones were perfectly put together? When I used to go to the museum and see it, how did they know if you were bones or statues?
So if you didn't hear the question, I just made the argument that we rarely find anything more than a few little scraps, and we're lucky to find that. And so the question is, how do the museum folks put together these spectacular big dinosaurs? In other environments, like for example, there's a formation that occurs in Colorado and adjacent states called the Morrison Formation, which is uppermost Jurassic, which is not a sand dune environment, and it's a river deposit, but not quite the floodplain apparently that we had here in Valley of Fire. And there you actually get whole dinosaurs that get preserved intact, or more or less intact. At Dinosaur National Monument in northeastern Utah, for example, there's spectacular. They built the museum right over the outcrop, so you can walk into the museum and see this big, huge bedding plane with fossil dinosaurs all over it. So there are circumstances, which we don't happen to have here in southern Nevada, where the dinosaurs are preserved intact. And apparently the situation at Dinosaur National Monument in the Morrison Formation is the dinosaurs died and got washed downstream and were buried quickly enough in fine-grained sediment to get preserved. And so this takes just the right set of circumstances. We just haven't found that yet here in Nevada, so I just don't think we had that circumstance. But in certain examples, certain circumstances, they actually do get whole dinosaurs, or nearly whole. You get maybe two-thirds of one preserved here, and then a third of one somewhere else. And what the museum folks do then is take a head from one specimen and put it together with the body from another specimen. And once in a while they make mistakes. There's some classic examples of mistakes about doing that. But in general, the museum people do a great job of trying to put together for the visiting public what these dinosaurs look like. But they'll almost always, it's going to be a composite. A big spectacular display in a museum will almost always be a composite. In our own museum right here, the Columbian mammoth, which was just recently named Christopher, that's one that's almost completely intact specimen that came from a site. The original, this is a cast, but the original came from a site in Utah. But the ground sloth, which is just right around the corner, which was just recently named Molasses, right? Is also came from southern Nevada, but it's a little bit more of a composite. So even though most of the skull, for example, in that particular ground sloth, which was discovered by Helen Mortensen, I don't know if Helen came in, but the skull was smashed in that specimen that is reconstructed here in the museum. So they had to bring a skull from had to take a skull from another specimen to put it on the post-cranial bones from that specimen, and so on. So almost always, the museum displays are composites of different specimens. So that's a great question. Was there any intelligent? In the pre-Triassic period, were there debates about global warming? There was certainly plenty of climate change and plenty of interesting animals to experience that. So we get the earliest amphibians and reptiles and lots of fish and, of course, lots of marine animals, trilobites and ammonites and all those guys. I doubt that there were any serious debates about climate change. Okay, I think we'll end it right there. Thanks very much.